Good morning. I would just like to take this time to help you begin starting to solve problems using your equations and graphs that represent constant acceleration motion. So we have a problem here. It says, while cruising along a dark stretch of highway at 25 meters per second, okay, so that would be important, 25 meters per second, which is about 55 miles per hour. You see at the fringes of your headlights that a bridge has been closed off with a barricade. It takes you half of a second to react, and then you apply the brakes and come to a stop 3.5 seconds later. Okay, so I think I can use those details to create a graph. Let's go for a velocity time graph. Yeah, that looks pretty good. So this is velocity. And looks like my units are going to be meters per second. Time is going to be measured in seconds. And let's see, you're cruising along a dark stretch of highway, and it looks like your speed is 25 meters a second. And it takes you half of a second to react. This graph doesn't have to be drawn to scale. So after half of a second, you start to apply the brakes, and you stop 3.5 seconds later. So that means it's not until 4 seconds you stop. So this is actually 3.5 seconds. Okay? Let's see here. So you have a constant velocity time period. That's when your speed doesn't change. All right? And then after that time period, so in this first section, we have constant velocity motion. In the next section, we have constant acceleration. All right. Let's see here. So I'm going to start here. Something like that. And okay, so we want a stack of graphs. Okay, let me draw a stack of graphs over here, small. There's one, there's two, and there's three. So that's acceleration, velocity, position. I'll just copy this graph over. We have this, and then this, right? So I just made a miniature version. Our acceleration's 0 in the beginning, and then it's some negative number here, because the slope of our velocity graph is our acceleration graph. And in the period where we have constant velocity, the slope of our position time graph should be our velocity time graph. But then after half a second, it looks like we have to slow down, so the slope has to gradually get less steep, something like that. Okay, so that's a stack of graphs. A diagram illustrating the situation. Okay, so there's a car. After half of a second, the car slows down. So in this second, this second, this second, the car is moving constant velocity. But then, at half a second, so the velocity is constant here. Then after that moment in time, the car just slows down. Okay, so these arrows have to get smaller. That doesn't look very good. I'm going to use the arrow tool because it'll look a lot nicer. I'm going to make my arrows a little bit longer. Okay. So the car is cruising down the road. On that. And then the car is going to start slowing down. Oops. Make the arrows smaller. And I'll put one more at the end. Oops. Did not want that. Whoa. Didn't want that either. Oh. And I'll make this arrow smaller still. So this is a motion map. And over here, we'll make this 5 seconds. No, half of a second. So 0.5 seconds. That's what that's supposed to say. So 0.5 seconds. So that's what this line is. T equals 0.5 seconds. And these are our velocity arrows. And this is constant velocity over here. And this is constant acceleration because our velocities are changing. It doesn't really matter if you're slowing down or speeding up. We always call that constant acceleration. Now, when we have arrows getting smaller, that means our accelerations are in the opposite direction as our velocities. So our accelerations would be towards the left in this picture. In other words, our accelerations are in the negative direction. Our velocities are in the positive direction. When acceleration and velocity are in opposite directions, you slow down. Okay, let's see here. What next? We got a diagram. We got a nice stack of graphs. We want to graphically represent the car's displacement from the first hint of danger until the car was stopped. Hint, area. Well, the area of your velocity graph, this area here, and that rectangle plus that triangle, that's going to give us our total change in position since danger was first spotted. Okay? So let's work that out. Let's figure out how far the car went during the time the person was reacting. That's this area here. And then the time when the car was actually slowing down. So let's find that total area. It's just going to be 25 meters per second times 0.5 seconds plus, now we need the triangle's area, which is that. That's going to be 1/2 25 meters per second times 3.5 seconds. So half of 25 is going to be 12.5. And the units become meters because the seconds cancel out here. So it's going to be 12.5 meters plus, okay, so now we need 12.5 times 3.5. So it's 1/2 0.5 times 25 times 3.5. I get 43.75. So 43.75 meters. And that's going to be, let's see here, that's going to be a grand total at 43.75 plus 12.5. I'm going to get 56.25. So I'm just going to call it 56 meters. And 56 meters, we should say 56 meters is the total change in position from when danger was first spotted until car was actually stopped. All right, so that's a pretty basic problem using your equations and graphs that represent constant acceleration motion. We actually didn't use any equations here, we just used the graphs, and that's where the equations come from, so that's fine. Anyway, hope you enjoyed it. Good luck on your problems, and have a good day.